So this is an important session for the Society. As many of you know, the Society takes great pride in awarding PhD theses and outstanding young colleagues. This is done through a nomination process where people submit their nominations and the President appoints a committee that evaluates each nomination. And once they make a decision, they are announced. Before 3 years, we used to offer the PhD awards only once every 3 years, but since the field is growing, we have now decided to offer it every year. So that is the reason why you see 3 PhD awardees here. And this year we also had an unusual but a good situation that the committee decided that we'll have a joint winners for also the Young Scientist Award, essentially. That is for a young scientist with outstanding publications. At this point, I should also thank Paulo, Alexandra, and the organizing committee for waiving the registration fees for the award winners. And the Society supports them through a prize award and also some a travel grant. So it is, I'd like to make 2 points. Colleagues that you have, students and young researchers, please nominate them. Only if they get nominated, they get considered, so please nominate them. It's a fantastic opportunity. And the next one is for all the awardees. With great awards comes great responsibility. So we look forward for your continuous support to the Society and to pay it forward to other young people. So please engage yourself with young people. They really look up to all of you as future leaders in this Society. The next speaker and the joint winner of the publication award is Mohamad Moosavi. He's a new assistant professor, probably not new anymore, but at the University of Toronto in Canada. Mohamad?
Okay, great. It's a great honor to be here today with you, and I want to thank Jose, Alexander, and also Arvind for organizing this. Yeah, I'm not that young anymore, 2 years old in the business of being assistant professor. So I quickly want to tell you about my past research and also a little bit of what we are doing currently and how the field of machine learning for adsorption material design is moving forward. It's good to be the last speaker of the session. Connor already gave the great introduction of why we are looking into these methods. There are so many adsorbents. Finding the best one for a given application is a headache. It's a hard problem to solve. And it's not just a specific problem to the field of adsorptions. It's about any chemistry, any material discovery problem that you need to explore large chemical spaces to find the best materials. And probably I get people in this audience to correct me, but I looked at the first adsorption isotherm that was measured on MOFs. It was 2005 that I found. And the first reported scalable practical material was 2021. This CALF20 material that was made by people in Canada. I'm proud to be in Canada now. So it took the entire community around 16 years to report this, probably a lot of failed experiments or a lot of learning went through this to make this discovery. We want to see if we can use AI to accelerate this process. And I'm a chemical engineer. The way I look at this problem is from this perspective that we have a problem to solve. It can be, for example, separating 2 gases or doing a reaction. For that, we come up with a conceptual design that would be designing a device or a process. And then after that, we have some KPIs to optimize, like we want to improve recovery or we want to reduce the energy penalty or whatever that we are interested in. What machine learning can do for us for material discovery is that it can help us to explore the chemical compound space, find the materials with right properties, and help us to synthesize them, that we somehow can optimize these KPIs. And to just show you how things can get fast in this field, I started this research in 2017, but like the first papers I have in this field is relatively old now. They're really boring to look at. So I tried to just pick one example from 2022 that helps us to understand how things are going. So we were looking into the heat capacity of porous materials, in this particular case MOFs, and heat capacity is relatively fundamental property of adsorbents. It's related to the lattice vibration of atoms. I'm a computational chemist. I look at the materials from an atomistic perspective. And it's relatively boring property of materials. It's like how much energy or heat you should add to increase the temperature of a material by 1 degree. So not many people looked at this. At the time that we looked at this problem, it was 2021. I think we could collect 4 or 5 experimental data, nothing more than that. So we thought, let's tackle this and see how much acceleration we can gain with machine learning. So we try to use molecular simulation density functional theory to compute the heat capacity. This is the curve showing how the heat capacity is varying with temperature. Increasing temperature, the heat capacity increases. The DFT results is compared with experimental data. There is very good agreement. There is one issue though, that is the computational cost of these DFT calculations is enormous. So this scales to n power of 4, n being number of atoms in a unit cell. So it was a very expensive thing to compute. We'll use a lot of compute in Switzerland. At the time, we had good computers. Still, we could generate around 200 data points for these materials, which was a bit challenge for doing machine learning on 200 data points. That's why we thought we should do a little bit more. We added one more thing to our machine learning study that was including some physics in the representation. So instead of just exploring the functional space that you have with machine learning, essentially representing any possible functions, we constrained it to some physics motivated equations. That is this CV equation that I'm showing here. That is linking the lattice vibrations, I showed you that, to the contribution to the total heat capacity of a material. And that worked pretty well. This is the prediction for the heat capacity. You can see on the curve on the right, and there was very good agreement between DFT data and the machine learning prediction. That was great. 2021 started the research. 2022, we could use this machine learning model to predict the heat capacity for MOFs, COFs, zeolites. And essentially, we have now this data that is out there. This is the predicted heat capacity for these materials. You see a large variation for some of them, like MOFs show large variation. Zeolites, very narrow range because the chemistry is the most dominant factor, and the chemistry of zeolite is relatively constant in contrast to MOFs. So, and then we went one step further. We used this for process simulation. We showed that, in fact, this can affect the ranking of materials. That's the eventual goal. We want to rank materials, find the best one for a given application. So in about a year and a half, we could start from 4 data points to all data and show it, in fact, it's an effective an important property. So this is the kind of thing we are talking about here, that in fact using machine learning can help us to move much faster than before. And that was the thing we used to do, mostly doing structure to property relationships. And I should say that the field of machine learning for MOFs, although we had huge progress, relied on the computational data that was generated using these crystal structures in Cambridge Structural Database, and also the computational ready databases like CoreMOF database or QMOF database. So that was huge. We could leverage a lot, but since I started my research group, we asked this question that actually there are much more to leverage in the literature. So we asked this question, can we leverage all knowledge available for a given class of material in machine learning studies? So AI systems that we are using so far are limited to the computational data. If you go to a conference like this or any chemistry conference, computational chemists are a very small audience. So can we leverage the other domain of data that we have access to? For doing this, we had to look at the history of material design and synthesis. This is our workflow. Usually we start with a crystal structure that is reported in CST. From that, we do computational chemistry. But before that, someone actually synthesized the material in a lab. They write a paper about it. They resolve the crystal structure and put it in CST. That's only one part of the thing they do. But they report a lot of interesting things about their materials. They put inside, they do experimental characterizations. So we thought if we want to be able to do this machine learning on all the data that is available, we need to link these two worlds together. But there is one issue there. The DOI of the paper is the only link between the crystal structures in CST and the actual papers. And when you look at the paper, there are many MOFs usually discussed. People use weird names for their MOFs, like CALF20 is Calgary framework, but how can you map that to a CST reference code, which is usually 6 letters? So that was a challenge to make this matching. We used large language model to do the matching. We get some hints from the crystal structure, like the symmetry of that was reported, the unit cell. These are usually the parameters that are also mentioned in the paper. If you have a large language model, it can read it for you and say, okay, this specific MOF with these identities is named like this in the paper, and these core references was used in this publication. When we have that mapping between crystal structures and this first workflow, when the mapping is done, the next step is to extract data from the publication. Now we know the names that are used to refer to the material, so that's an easy task. It's relatively straightforward. Use any large language model, it can do it for you, and then put everything together. And one surprising, or not surprising, but very impressive things we found was that when we try to extract data for around 10,000 papers, it's around 15,000 crystal structures, we found MOF fields is really extensive and diverse. About 23 unique application classes we identified from these 10,000 papers. So it's really, the question for us is, how can people in one field leverage all the knowledge in other fields? Like people here are interested in adsorption, this application of carbon capture, for example, gas separation, but there are people who look at MOFs for photoluminescence, for catalysis, for like electronic devices. Of course, the applications are different, but there is a lot of overlap in the characterization methods. You can see here the properties that are measured and reported for these materials for different applications that people can learn from each other. And that's effectively how human does this, but AI systems are not doing that yet. So to be able to do that, we put everything together. So we came up with this schema that is a graph-based, connecting all the dots together. You have a material, computational data, experimental data, source, synthesis procedure, and the names that are used to refer to this material, putting everything together, and then all the data that we extracted from the 10,000 papers, together with the computational data that we had, put everything in something we call a knowledge graph. That's nice. It's enabled us to do new things now. The first thing we can do is, going back to the old-fashioned machine learning studies, we train a machine learning machine learning model to do property prediction. Probably you have seen many models that predict CO2 adsorption isotherm. Now we have computational data and experimental data together. We can now, for example, predict materials that have good CO2 uptake, at the same time are water stable, because water stability is something we still cannot do with computational modeling. While people report some sort of water stability data, it's not perfect, but still some early evidence. This is a model showing, This is a model showing that the simple classifier can reach a good accuracy in saying a material is water stable or not water stable. This is the distribution of data. Interestingly, we found the reported water stability. People report mostly water stable MOFs, which is not the way we know this field, but it's mostly because probably report the positive outcomes, not the negative ones. So that's the way we used to do things. But recently, I think probably most of you have seen large language models becoming mainstream. People are using it for all sorts of cool things. And this paper, actually, the preprint for this came out last year. This paper, though, it got published yesterday in Nature Chemistry, where authors showed that if you ask questions from large language models and compare it to expert chemists, Large language models show superhuman performance. So they curated around 2,700 questions, asked people to answer them. The lowest human performance compared to average human, and the highest human showed compared to all sorts of models here. And you see that large language model on average show a better performance than human in answering questions in chemistry. But of course, these kind of things always come with a but, because that is more like looking at the general field of chemistry. Of course, someone who is specialized in a field like MOFs might know the field much better than the average chemist in the field. So what we did was asking this question, like, is UL-MOF5 water stable from ChatGPT, to see if in fact you can use large language model to do property prediction for MOFs. And these are the two answers I got from GPT-4o. Actually, the first one is GPT-4o with search. It does the web search. The second one is GPT-4o vanilla without any variation. I also did it with deep search, which actually looks at the papers in the literature and tries to answer. None of them could answer this question. And you see the hallucination there. That's the scary thing. It comes up with nonsense but reasonable answers. If you don't know UL-MOF5, it's actually ultra-light MOF5, but it says it's University of Louisiana because many people use the name of university to naming their MOFs. And the other thing is that, for example, it says it's a variant of MOF5 because it's similar in name. But it has nothing to do with that because it's a lithium-based MOF. So we said, okay, we have a good platform now. It's a knowledge graph that actually condenses all the data in the literature. Can we augment this with large language model to make a literature-informed AI assistant? So this is basically very simple workflow. We ask a question, LLM, query the data, extract information, pass it to another LLM, provide you the answer. And here's the answer that we got from our system. It shows that UL-MOF5 is not water stable as indicated by its property being unstable in water. This is justified by text that states UL-MOF5 is soluble in water and methanol and gives a reference to you. So where is this coming from? This is actually coming all from the knowledge graph that was resolved and extracted. And in fact, if you look at that publication, you see that exact sentence, that this material is soluble in water and in fact not stable. So I think this is a very exciting time to use this type of systems to do material design. We did a survey. We asked about 10 expert MOF chemists from different universities to help us to score and evaluate our AI assistant compared to ChatGPT. This is the evaluation that they did. They gave overall much higher score to our system compared to vanilla ChatGPT or normal ChatGPT that you have. All right. So this is an award talk, so I shouldn't just talk about science. I just want to say about my story here. I started in 2017 looking at MOFs. And at first, we started looking at the topological and chemistry descriptors for doing a structured property relationship. Later, we were the first looking at robotic platforms for synthesizing MOFs. At the time, I was a computational, and I'm still a computational chemist, so I didn't continue that line of research using robotic platforms, but we are now doing it again. We did analyze the diversity of these databases, a lot of insights from that, and also property prediction for all sorts of properties like heat capacity that I mentioned. We recently showed Bayesian optimization to automate these platforms, and also these three papers that we recently worked on: multimodal learning, agentic platforms, and also this MOF community, this unifying data from experiment and computation for MOFs. But of course, this is not done in vacuum. This was done with really great people that I had the privilege to work with. I every day got inspired from them. I learned from them and could effectively work with them. That's why we could do good work, I would say. That's why I probably got the award. These are few of the people I had the privilege to work with. My supervisor, Bernd Smith, was a big inspiration for me. And Arvind, at the beginning of this session, mentioned that people who receive the award should continue giving back to the society. I already started that. This is my team, and I'm training the next generation of the people working in this field. And we are at the University of Toronto, 2 years old, but full of energy, doing research in accelerated AI for material discovery. Thanks so much for your attention, and I'm happy for answering questions.
Thank you.